Chapter 10, Section 2, where we are going to discuss today the relationship between the mole and the mass, and the mole and the volume. Of course, last time when we had the first section, I just want to confirm in a couple of things that whenever we want to calculate the required or the needed value, we have to use convergent factors. That is the idea behind, introducing the mole, which is a unit that contains a specific number of representative particle, which is Avogadro's number. The other important thing that you need to carry with you from section 1 to this section in order to understand is the fact that how to calculate the molar mass, or the meaning of the molar mass. The meaning of the molar mass, that is the mass per 1 mole. So we have here a convergent factor that we will be using today, and that is the fact that the molar mass is basically the mass of 1 mole. So for each or any substance, if we can calculate the molar mass, then we can calculate the moles. And that is the idea behind the first objective here, is to describe how to convert mass of a substance to a number of moles of a substance, and moles back to mass as well. So we can go from moles to mass and mass to moles. And I guess that this is the most important conversion that you will need for any calculation in chapter 12. When we go to chapter 12, as I said, and we start calculating the amounts of reactants needed and how much products will be produced, indeed, we will be dealing with grams and moles only. Sometimes we may go into volumes if you're dealing with gases, so that's why comes objective number 2, which is how to convert the volume of a gas at STP. STP is a standard temperature and pressure. We will learn today why it is an STP, because if it's not STP, then we might have some issues with that relationship. The last part is the conclusion, or as a result of understanding objective 2, then you should be able to use the molar mass and the gas volume, or of a gas, and the molar volume, which is already we know how we will learn how to calculate as per objective 2. Then you can use that to calculate the density of the gas. We will see that. So here's a general example. Well, the question is, how can you calculate the moles of a substance in a given mass or a given volume? Yani, if we give you grams, let's say 10 grams of potassium, how many moles are that? It is similar to what you see in the picture in front of you, which is if you want to count how many pennies are there, I think it will be difficult, maybe. It's not impossible, but it will be harder to empty the content of this bottle and start counting one by one. Instead, what you can do is what? What is your suggestion in order to guesstimate, so to speak, how many pennies are inside that jar? What do you think you can do? Okay. Weigh what? We have to weigh the whole thing, or just one thing, or what? Separate them, maybe? Well, we said that we don't want to separate them, yeah, Judy. That's the idea behind this. Calculate the moles. Well, there's no moles here, yeah, Faisal. Then divide the jar by the mass of 1. Yes, I think that is the correct answer, is that you weigh the whole jar and you weigh 1 penny and then divide the whole by that. That will give you an estimate, of course, because there's the mass of the glass and stuff like that. But you have to weigh one of them and weigh the whole thing and divide this by that. Then you're going to get the number of So if we, I mean, to copy this in what we are doing, then I can calculate the moles of any substance if I know two things. I need to know the molar mass, and that is, in this case, is equivalent to the mass of this whole jar, and the mass that I have, which is the mass of one penny. If you divide the mass of that penny divided by the total mass, that will give you how many, the opposite, I'm sorry. The mass of the whole jar by the mass of one penny, that will give you the number. It is the same thing in the case of the, anyways, I think it's a good example to introduce us to the mole mass relationship. Okay, that is very important relationship between moles and masses of different substances. Now, it is good to remember, although I talked about this last time, but just to introduce this to you again. Whenever you have a problem or a question where we're talking about the 7 elements that exist in a molecular form, meaning H2, O2, N2, Cl2, Br2, I2, all of these twos, or dimolecular, bimolecular, if you wish, by diatomic molecules, I'm sorry. You have to be specific about the molar mass. When we say molecular oxygen, that means that we're talking about 2 atoms of oxygen. But if we're talking about atoms of oxygen or 1 atom of oxygen, then that is 16. So you have to be just careful about how to do that. All right. Going back to the molar mass and the of an element or a compound, regardless. Last time we learned how to calculate that, and we said that for the molar mass of an element, which is the mass of 1 mole of that element, we can find it from the periodic table as the atomic mass. For the molar mass of a compound, if we know the molar masses of the element that are making the compound, like for example H2O, then we can calculate the molar mass of the whole molecule, which is 2 times the molar mass of hydrogen plus 1 times the molar mass of oxygen in this case, which is total of 18. So that is the molar mass of water, and that's why we call it 18 grams per mole. And that is the relationship that we want to use. So we can make a conversion factor from that, which is the molar mass divided by 1 mole, or 1 mole divided by the molar mass, right? So we, again, it's red and green, but that is just to distinguish between them, not, in the exam, some of you might say, well, where's the green or where's the red? Okay, so from the idea of the molar mass, which is the mass of 1 mole, we can create these 2 conversion factors. Now, why we have these 2 forms? Because sometimes we have a mass as a given quantity, then we multiply this over here, right? Because if you multiply the mass with the molar mass, the mass goes with the mass and you end up with moles. But if you have the moles and you want to convert it to mass, you can use this one where the moles goes with the moles and you end up with a mass. So again, we have here 2 conversion factors, and we need to be smart enough to decide which one to use. It depends on the given quantity, as we discussed last time. So depending on what you have in your hand, you can decide what to do. Let's take a first example and see. Items made out of aluminum, which is, using aircraft parts, cookware, blah, blah, blah. That is all introduction, but this is the most important thing, which is aluminum oxide, which is Al2O3. This stuff resistant coating prevents any further corrosion. Now, here's the question, which is in red. What is the mass in grams of 9.45 moles of aluminum oxide? So what we need to do, the case of a numeric problem, as usual, we have to analyze. What we analyze is the following. First of all, we know the formula of the compound, and hence we can calculate the molar mass, right? Which is 2 times aluminum and 3 times oxygen molar masses. And then also we know the moles that we have. What is the unknown? The unknown is the mass of that equivalent to the 9.4 moles. That's what we need to calculate. Now, since we have moles, then which conversion factor we're going to use? Is it the this one or this one? The green? Yes, the green. Why? Because we have moles. هل هذا مظبوط يا محمد؟ ساعدوني. أنت عندك moles. How could you use the green? Then your answer, well, it is the red. I'm just saying that green is wrong. Usually when I get an answer from somebody, I go with that. So we just want to find out that it is wrong. So when we have the moles, we cannot use the green. We have to use the red, ya Muhammad. Why? Because we multiply the moles here. The moles goes with the moles and you end up with mass, and that's what you're looking for. Okay, so in this case, here's the analysis. This is the number of moles, and that is the mass that I need to know. I need to go from moles into mass. Okay, so this is the way we calculate the molar mass. Again, it is 2 moles of aluminum times 27 by 1 mole, that is 54. This is coming from the periodic table. 3 moles of oxygen times 16, that is 48, and that is again coming from the periodic table. So we end up with 102 grams per mole. Okay, so we have that conversion factor. This is our conversion factor. All what you need to do is to multiply here by 0.54 mole, and the mole goes with the mole. So we're talking about almost roughly about 960 maybe of grams, right? Yeah, 964 as a matter of fact, which is 100 times 9.4. Of course, yes, you need to do use the periodic table, yeah, Judy. Yes, and that's why we provide the periodic table in every single exam that we have. Okay, so this is the answer that we get. Now, what is the third step in this case? After when we do numeric problems, what we do next? We evaluate our answer. Yeah, the units are grams, that's fine, but we have to evaluate our answer. Does it make sense or not? Usually, in order to evaluate, we said that you make the numbers like whole numbers. Instead of 102, make it like 100. And this is like 10. 10 times 100, that's 1,000. And this answer is closer to 1,000. So that is the way we evaluate it. Okay, so around 1,000 grams. If you get something here that is, for example, 9 grams, then you know that you're wrong. If you get 9,000, then there's something wrong. If you get something 700, then that's the way, the meaning of evaluation, which is to see if your answer does make sense or not. Here's another example, and I want somebody to give me a plan of how to do that. Now, remember that the analysis is basically what are the unknowns and the knowns. Then we have the plan, which is, are we going from mass to moles or moles to grams? Then which conversion factor you are going to use. Then you implement that, you get an answer, and you evaluate it. That's the whole thing. So when iron is exposed to air, of course, you know that it corroded and turns into a brown, rusty. I think the rusted iron is iron 3, so that is Fe2O3. Now you see how the information that you learn in chemistry 1 is very important, which is when you say iron 3 oxide, if we do not provide this one, you should know by default that it is Fe2O3 in order to make it a neutral compound. Anyway, how many moles of iron 3 oxide are contained in 92.2 grams of pure iron oxide? So what is the known and unknown? We are from the mass to moles. Okay, we have to do mass to moles. That's what you mean, Faisal. Okay. Now هلا هنا I'm afraid that يعني I'm using the red and green for your help, but not يعني تصيروا تعتمدوا عليها بعدين تضلوا تقولوا green or red. Yes, that is true. We're going to use the one which is in gray. So that is uh, um, 16 times 3 and 27 times 2. منين جبت 27 هاي Eileen? Iron, did you check that? Anyway, هاي الإجابات المتسرعة sometimes might get you in trouble. Okay, so what we have is a mass which is 92.2 grams, and we have the iron. See, the iron is what? 55.8. Yeah, Eileen, it's not 27. I don't know where you got the 27 from. So that is 111.6 grams of iron and 48 grams of oxygen. The total is 159.6 grams of, what is this? This is the molar mass. So if that is the molar mass, then this is our conversion factor, which is 1 mole of iron oxide weighs 159.6 grams. Then whatever grams we have, which is the 92.2, will be multiplied by this. Now, roughly how many moles do you think that? Is it up to 1 mole or less than 1 mole? Before you get to see the answer, I mean, when you're doing the calculation, it should be less. Why? Because the 1 mole is 160 almost, and we have 92.4. طيب, what do you think the value should be? I mean, before you do the answer, is it going to be, we know that now it is less than 1, so is it going to be more than half or less than half? More than half. Why? Because if the 1 mole weighs about 160, so the half a mole will be 80, right? So that is 92.4. So you can know that it will be more, before you do the calculations, that it will be more than 0.5. And that's why it is 0.578. So you already evaluated the answer before you go into the second slide that it is correct. How do you know? Because we can make this 160. That's the only way to make this 160 and make this 80. Then it should be around 0.5. But it is a little bit more than 0.5. Why? Because we made the 9280. So that is a little bit more than 0.5, and that is a correct answer. Okay. So why I'm doing this with you? Because in your exam, for example, when you're doing your calculation and looking at the answer, it's not always the case though, but you will see that some answers can be excluded from the choices that you have immediately by looking at this formula. For example, let's say the answers are this one, which is 0.578, and that is choice number A, but choice number B is 1.5 moles. So immediately you exclude that. And you have something which is 0.1 mole, you exclude that. But if there is something very close, then you have to get the correct one or the accurate one and then make your judgment about it. Okay. So if you do that, it is 1/2 of the mole, and that's the way we'll evaluate it. طيب. You know, this is an assumption question. You know how many grams, okay? You know how many grams of a substance you have, and you want to find out how many moles this is. What other information do you need to know and where you can find it? It is the molar mass, and you will can calculate from the periodic table. So it's not, yeah, that is true. The molar mass is needed, and you can find it from the periodic table. That's where you can find or calculate the molar mass. Okay. All right. So we took two examples. I think this is fully understood now that you can play between moles and grams using the, if depends on the amount given, whether you have you have a mass that is provided, or you have your moles provided. Either one of them can be used to calculate that, and that is by using the molar mass relationship. Okay, now we're going to move to the mole volume relationship. Now, can we do the same thing as the molar mass with all the material? No, it's only with gases. Let's see why is that. Take a look here. These are three materials. One of them is liquid, the other one is solid with large particles, the other one is solid with small particles. And these are the glucose, para-dichlorobenzene, and I guess that is water. So look at them. These are 1 mole of each, but look at their volume. That is completely different. So different solids and liquids definitely will have, or 1 mole of different solids and liquids will have different volumes. Their volume is not going to be fixed. But in the case of the gases, that is a different story for a reason that is related to the nature of the gases, which is unlike liquids and that, the moles of gases, they have, under the same physical conditions, though. If we have same physical conditions, يعني, let me show you, there's a picture there I will show you. Avogadro's hypothesis, which states that equal volumes of gases at the same temperature and pressure will contain equal numbers of particles. Before we move to the next slide, does anybody know why, in the case of the gases, it doesn't matter how big or small the size of the molecules, they will occupy the same volume? So you saw that in the case of the solids and liquid, that 1 mole of different solids and liquid will have different volumes. But in the case of the gases, if the temperature and the pressure are fixed, then different gases or different moles, different 1 mole of different gases will have the one volume, the same volume. That is for a good reason, which is the fact that the spacing between the molecules of the gas is huge, to the point that having large or small particles of the gas will not affect the volume. Okay, not because they're not organized, because they have empty space between them. And that is due, of course, to the lack of intermolecular forces. Let me just give you another good example that might bring it to your brain much more easier. Now imagine that we have a room, the room that you're sitting in, okay? If we put in that room 100 basketballs, will the room fit for that? Yes, right? What about if you put 100 tennis balls? They will fit too, assuming that these are gas particles and they will be floating around. The basketball gases, they were okay with the size of the room, occupy the whole room, and the 10 balls of tennis, they also occupy the room. And that is because the spacing between them is the same. If you want to read this sentence, relatively large particle does not require much more space than the same number of relatively small particles. أحسن شيء to look at these two shapes, which is A and B. See, that's the room I was referring to. You see, this blue one is a gas with the small particles. And the one next to it is another gas, but with the larger. But since there's plenty of space, both of them, they occupy the same volume. Okay, as long as we have one thing fixed, which is the temperature and the pressure. If any of those has changed, then the volume will change. Okay, so that's why they choose the standard temperature and pressure in order to calculate that. So they took a gas, any gas, and they fixed the temperature to 0 degree, and a pressure of 1 atmospheric pressure of 101.3 kilopascal. These are the standard temperature and pressure. Okay, and that is the this is the temperature and that's the pressure. If we have a gas that is in a container at these two conditions placed in here, the volume that the gas will occupy found out to be 22.4 liters. Okay, but that is under STP only. So for gases, we have what we call a molar volume. So this is the volume occupied by 1 mole of any gas at STP. So from that we can generate a conversion factor. So the quantity of 22.4 is called a molar volume of gas because it is for any 1 mole of gas at STP will occupy the same volume, and that will generate these two conversion factor. Again, we have red and green ones, which is 22.4 per 1 mole and 1 mole per 22.4. Which one we will use depending on the quantity that we have. So again, we can go from volume into moles or moles into volume. And that is specifically for gases, and not any gas, but the gases that are operating under standard temperature and pressure. In the case of the previous one, with the molar mass, there's no requirement. I mean, there's no condition. Either it's a gas or it is a solid or a liquid or whatever it is, we have 1 mole per the molar mass per the 1 mole. And we use that to play back and forth between the moles and the masses. And in the case of the gases at STP, we have 22.4 liter per mole, and that can be used as a conversion factor. Okay, so if we know the volume, we can convert it into moles, and if we know the moles, we can convert it into volume. Here's an example. Sulfur dioxide, which is SO2, is a gas produced by burning coal and the air pollutant, blah, 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 blah. Determine the volume in liters of 0.6 mole of SO2 gas at STP. So what is the known values here is the moles. So we have the moles, right? And we need to calculate how much is the volume, determine the volume. So our answer should have a units of liters. So we have 0.6. We know that 22.4 divided by 1 mole can be used in this case. Okay, so that is what is known for us, is that we have 0.6 moles, and we have 1 mole is occupying 22.4 liters at STP. So if that is the case, then what is the volume of 0.6 moles? And let me ask you this now. Do you think that the answer should be more or less than 22.4? It is less. How did you know that, Muhammad Saaduni, that's going to be less? How did you know? Because راح انتظر معلش. محمد قول لي ليش, why do you think it is less? I know it is less. It is going to be 13 liters. But before you do the calculation, why it is less? Because it's multiplied by 0.6? That's not a good answer, ya Muhammad. I know it is correct, but you should express it in a different way. You should say that 22.4 liter is the volume of 1 mole. And since we have 0.6, which is less than 1 mole, then the volume accordingly will be less than 22.4. Okay, not because we multiply. هذا جواب الحافظ وليس جواب الفاهم. This is an answer of somebody who tried to memorize. I'm not trying to underestimate your يعني participation محمد. بالعكس, you are a great student. You are participating on all the answers. But I'm trying to teach you the right thing. Okay? So your answer is correct, but it has to be framed in the right way. And that right way indicates whether the student understands the concept. Remember my advice to you, and now it is becoming more important in the case of chemistry too. Understanding is much more important than memorizing. There is no memorization here. You have to understand the concept. Thank you very much, Muhammad. Okay, so this is the one we're going to use, and we multiply it 0.6, and that is 13 liters. Let's take another. Of course, the answer is correct because it is for that. Okay, طيب. Now let's move to the last part, which is the density. You know what the density means? It is the mass per volume. Okay, mass per volume, unit mass per volume is what is we call as the density. The density of, for example, solid objects compared to, you know that if you have a piece of iron, you place it in water, it will sink. But if you have a piece of wood, it will float. That is because wood has a lower density than water, iron has a higher density than water. In the same way, in terms of gases, because this is the calculation that we're going to do here is related to gases only under STP. Can we calculate the density if we have an air balloon that is filled with gas, depending on the on the density? And a very good example for that will be if you attend or you are planning to or you are organizing one of the parties where you use balloons. Now these days people, they will go to the shop and they fill it with helium. Why do you think they will fill it with helium, not with blowing their air inside, whether using their mouth or any other pump? Why do we use helium? Hmm. Anybody knows why we use helium in the parties when we blow up the or fill up the balloons? طيب, less dense, and that will help us to keep the balloons all the time up. انت مش معقول you want to run it's not lighter, it is less dense ban. We don't use the word lighter. We have say it is less dense. The density is lower. So because the density of helium is less than air, then it will be up in the ceiling, and that's what you want. You don't want the balloons to be floating on the ground, right? So for that reason, we use helium. طيب. We go back again to the density. It is mass per unit volume. طيب. هذه اللي هي density. طيب. Even if we know any of two of these three, whether we know the density and mass, we know the volume and density, we know the mass and volume, we can calculate the third one, right? Okay, so what we have in the case of STP, we have 1 mole, and that has a mass, which is the molar mass, right? And we have that 1 mole also has molar volume, and that's 22.4 liters. So for any gas, if I know the formula of the gas, let's say, for example, O2, okay, that is the molar mass is 32. And I know that 1 mole of that weighs 32. And I know also that 1 mole of oxygen will occupy 22.4 liters. So here I have a mass and I have a volume. And that's what I need to do. Just divide the mass by the volume and you will get the the density. So the density of a gas under STP can be easily calculated, or the molar mass of a gas, of a known gas, can be calculated if we can measure the density. Either one of them can be used to calculate that. Again, let me repeat. The density is equal to the mass over the volume. If we have a gas under STP, first of all, any gas will have a molar mass. And that is the mass of 1 mole. So I can put this in here. And also, since it's under STP, 1 mole will occupy 22.4 liters. So this one can be 22.4 liters. So I can calculate the density. If I provide you with the density and I tell you any gas that has density of 1.5, then you know for sure that the mass of that gas is 1.5 times 22.4 liters, because you substitute. Anyways, let's take an example and we will learn from there. The density of a gaseous compound containing carbon and oxygen. So he's telling you that it contains carbon and oxygen. That's an information. And also, the density is equal to 1.964 gram per liter at STP. What is the molar mass of the compound? So what you do is the following. I mean, this is the simplest way, regardless of how the book is putting. It's the same thing. But the density, we say the density is equal to 1.64 grams per liter, and that is equal to the molar mass that I'm looking for, divided by 22.4 liters, right? So the molar mass is equal 22.4 liter times this one, which is going to be 1.64 grams per liter times 22.4 liters. The liters goes with a liter, and that is going to be 1.6, yani, roughly, let's see the answer, what is when you do the multiplications like what we did here, then you end up with 44 grams per mole. The answer is 44 grams per mole, and that is containing carbon and oxygen. So the question is, what do you think the gas is? What kind of gas is this? What gas specifically is that one? How would you answer such a question? You do trial and error. I mean, what kind of gases that contains carbon and oxygen usually we deal with? Either carbon monoxide or carbon dioxide. If we consider carbon monoxide, which is CO, right? If we consider CO, that is 12 and 16, a total of 28. So that's not the one. But if you consider carbon dioxide, then we have 12 plus 16 times 2, that is 32, plus 12, that is 44 grams. So the gas that we're dealing with is carbon dioxide. Okay, so here we had the density and we were able to calculate the molar mass. Sometimes we have the name. We say, for example, as an example I've given you, which is calculate the density of oxygen under STP. What you will do is you will have 32 divided by what? By 22.4 liter in that case, right? Okay. Right. This is this is the conclusion of the whole chapter here. Okay, not only for this chapter, but also from chapter 1. I mean, I'm sorry, from section 1. All right, let me just move this over here so I can see that. You see this, I don't know what you want to call it. It's like a plane, okay, airplane. All right, here's the mole sitting in the, as a central unit, sitting in the middle. You can go back and forth into number of particles as per what? As per what we have learned in section 1, which is 1 mole divided by Avogadro's number, or Avogadro's number divided by 1 mole. Back and forth between moles and particles. So either we have particles, we can convert to the moles, moles can go back to particles. The same thing we can do with mass using the molar mass, going from mass into moles back and forth using 1 mole of any substance divided by the molar mass, or the molar mass by the 1 mole. We can do the same thing under STP between the volume and the gas, the volume of the gas and the moles. So we can go back and forth, right? So we can take the particles sometimes, instead of saying, what is the density of oxygen? I could tell you what is going to be the density of, for example, 200 molecules of oxygen. So what you need to do is to go from the 200 particles from here into moles, and moles into how much is the volume, and from the number of particles and moles you can calculate the mass, divide the mass by the volume, and you get the density of that specific number of particles. Or يعني you can go anywhere from anywhere. بدك volume لmass, mass to particles, using these convergent factors. The convergent factors again are written for you over here. Okay, here they are. This is the convergent factor that will take you from the particles into moles. This is the one which will take you back from moles into particles. This is the molar mass over 1 mole, will take you from the moles into grams, and grams into moles using this one. This is the one which will take you from the volume into moles, and moles into volume. Okay, so understanding this shape and the three convergent factors along with their other form that will make it a total of 6 convergent factors. Don't memorize them, but rather you need to understand their concept, and I'm sure that with understanding their concept you will be able to solve any problem that has to do with these kind of calculations. Okay. طيب, what is this? This is a question that I already answered for you, but I want to check who still remember that. Why does 1 mole of any gas occupy the same volume, which is 22.4 at standard temperature and pressure? Why? نسينا? We forgot size of the particles? Because of the size of the particle, يا غيدة معقول? Because the plenty of space available between the particles. So the size of the particle is no importance here. Okay, because the gaps, yes, because it won't change the volume. Being big, being small is not going to affect the volume due to the large size. Diamond, remember that a room where you can put 100 basketballs along with 100 tennis balls, both of them will fit in the room regardless of their sizes. Okay. All right, that's the end of it. This is the end of section section 2. Do you have any questions? Any questions? Any concerns? Anything? Very good. Well, you will be lucky this weekend, since it's the first weekend in the semester. We don't have homework. Because usually we finish the chapters by Thursday and we give you the homework. So the homework for chapter 10 will be released after we finish it, inshallah, on Sunday. One other thing, I will see some of you on Sunday, because starting Sunday, I will be delivering this lecture from the classroom. Whoever is interested, that's good. Inshallah, بس ما تكونوش كثار. يعني hopefully they're not gonna go beyond 20 students total. But anyways, we will deal with whatever we have. Remember that when you come in here, if you decided to come, you have to wear your face mask all the time, keep the social distancing inside the classroom and outside the classroom. Okay, have a nice weekend, and I will speak to you, some of you, and see some of you on Sunday. All right. Yeah, thank you. Bye.